Again, my name is Kridler, and I'm a data scientist on the merge algorithms team here at Stich. And so tonight I'm going to be talking to you about what I'm calling feature discovery. And it's the idea of feature engineering through iterative model building. So as you build a model to learn from what comes out of it, and then use that to add to new features. So a little bit about me. I went to grad school for applied math in University of Colorado Boulder. I decided not to get a PhD and left with sort of a consolation prize as a master's degree. I worked in defense for like 7 years, mostly in remote sensing, ocean physics and radar, image processing, all that sort of thing. And so one of the challenges of working in defense is that you can't talk about anything that you work on. And so when Kaggle came along, it was great because it was like, here's a chance for me to show what I use in my day-to-day work on problems that are available to the public and that I can actually talk about. And so from working on Kaggle, I ended up going to healthcare for a little while, and then eventually came out to the Bay Area, and now I'm at Stich. And again, I'm on the merge algorithms team, so focus on everything relating to our inventory. In a sort of broader sense, I do feature engineering for the health of our inventory. And to support that, I open sourced I guess visualization helpers for building dashboards called Pixely. It's in Python. So in this talk, this is just a brief overview. I'm going to talk a little bit about feature engineering and domain expertise. I have a little call out to the Drew Conway's data science Venn diagram, my feature discovery process, Kaggle competitions, and this right whale detection challenge that I worked on, and then talk about when this process actually works and the kinds of problems that you should use it on. So when data science started becoming popular, there's this really popular Venn diagram from Drew Conway that showed that at the middle of hacking skills, math and stats knowledge, and domain expertise, you have data science. And I would argue that there are great tools as far as the hacking skills in math and stats. We have R and Python and the whole stack that's been built around data analysis for that. But domain expertise is actually a barrier, right? So a lot of times people go into solving problems and they really don't know where to start. And so there's a lot of machine learning research to try to get around that. But for the most part, someone who has a little bit of experience in an industry can build a really simple, high-performing model without too much effort. And that still beats like deep learning and things like that. Deep learning is getting much better, but depending on the problem, you can still get away with some really simple things. So the goal of this talk is really to get you to focus on the data and not on the algorithms per se. And the reason they want to do that is because you can still do machine learning, but you still sort of learn from the machine learning as you go. Why focus on the data? Because you can actually build domain expertise as you go. So you may start a problem knowing absolutely nothing, and then at the end of it come out building a model just as good as somebody who had a lot of domain expertise, right? And so before I jump into that, I thought I'd share with you what is feature engineering. And this is Google's definition. And it's just the process of using domain knowledge of the data to create features to make machine learning algorithms work. And so now I'm going to go over what my feature engineering process is, which is a lot like the game of set. Are people familiar with that game? OK, so in the game, you lay out some cards. And the goal is to find matching sets of 3 cards that follows like the rules of the game. And the way it's like set is that if you think about predictions, and like maybe you've decided that you're going to only look at a certain group of predictions, that's a lot like laying out the cards. And what you're doing is looking at how your algorithm is performing and trying to use your like innate ability to recognize patterns to build additional features. And so you might think like, OK, here's your deck of set cards, and you're looking for these like group of 3s. And so now you have gained a little bit of information. You remove that from the group, and then you draw some more cards, or in other words, like make some more predictions, and then you go again. And so this is basically the flow that I take, which is find some way to visualize the data, look for patterns, particularly ones that are, I don't know, larger proportion than others. You don't want to just find like small things. You're looking for big effects, and then iterate. All right, and so to illustrate that, I'm going to walk through this Kaggle right whale challenge and talk about how I approach the problem and how I use this process, and then what the ultimate result was. And so just as a quick recap, the whale challenge was this competition where they provided you with something like 80,000 2-second audio clips. It's like 4,000 pulses. And on the competition website, they transformed that audio clip into what's called a spectrogram. It's a time, frequency, intensity plot that's made using these like short FFTs, fast Fourier transforms, if you're not familiar with that. And in this image, you can see there's this sort of arced feature that's much brighter than the background, and that's what they're looking for. So the goal of this was to build a detector that finds whales or correctly classifies whales versus non-whales, and then maximizes the area under the curve metric. And I'll talk about that in just a second. But going into this competition, since I was a mathematician, I knew what fast Fourier transforms were. I had some experience with Python and OpenCV since I worked on image processing. But I didn't know anything about whales or audio data or spectrograms or speech recognition. So I sort of was taking this from a pretty novice approach. And just for reference, so the area under the curve metric they provided was from a Cornell University benchmark of 0.72. So that was what people were tasked with beating. Right? And so I started out with the simplest model that I could think of. Turns out other people try to, this wasn't as obvious as it was to me, but I took all of the samples that were labeled a whale, and I averaged them together. And what I saw was, sure enough, you still see that sort of arced feature in the center. And if you do this for the clips that don't have a whale in them, you don't see the same kind of effect. It's just sort of washed out. So my first thought was, well, what if I just take this chip out here that I've outlined in the center, and I calculate the cross correlation with all of the other samples, right? So basically what I'm looking for is a match template between this, average spectrum and the raw data. And then from each of those, I can figure out where does the maximum occur and what is the maximum value. And so I have a max correlation metric. And each of these plots I have, the red is the right whale distribution of the particular metric, so correlation is at the top, and then the locations of those maximum in frequency and time. And so right away, it looks like there's some separation, at least in the correlation, which means that my initial hypothesis was correct, that it's not this sort of feature is not going to be very strongly correlated with the non-whales. So when you do that and you build a simple classifier, whether it's like, I even did a linear discriminant. I think for this I used a random forest with like 3 features. You get an area under the curve of 0.92, which is already 20 basis points above what the Cornell benchmark was. And so for those of you who are not familiar with the area under the curve, basically you have this receiver operating characteristic curve. The dotted line represents an area under the curve of 0.5. It means that you have your probability of correctly classifying is the same as a coin toss. And so moving away from that line towards the upper left is the best possible scenario. And so already we were doing pretty good. And so on the left here, I've got probability densities of the right whales versus the non-right whales. And you can see there's a lot of separation. But really what I'm interested in are these whales that I've missed, because I've got sort of this long tail and I'd like to understand why. And so the first step is like, let's draw some cards, right? And so what I've done is visualize some more spectrograms of the ones that I got wrong. And I try to identify a pattern. And the first thing that jumps out at you is you can't really see anything. But then if you do some contrast enhancement, the signal jumps out pretty well. And so the first step, or the first pattern was, okay, for some of these, I have a weak signal. For whatever reason, I'm just not seeing the thing that I think is going to be there. And so that was the first learning. And when you apply that and you go through this process again of the template correlations, you see that you shift the distributions further apart. And so the dotted lines are the original correlations without the contrast enhancement. The solid lines are with the contrast enhancement. And the most important part is just that the red's moving further to the right and the black's moving further to the left. And so what that does is gives you an area under the curve of 0.94. So already, I wasn't anywhere near the top of the leaderboard with this, but it wasn't bad for a few hours of work. Right? And so basically, I just continued this process. And I made a lot of submissions. There's even a deep learning post that comments about how many submissions that I made. But so I choose an algorithm, generate a model, evaluate that model, look at where I'm doing well and where I'm doing poorly, turn those ideas into code, and then just keep doing this loop over and over again. And so I focused on quick iteration and what could I learn in a short period of time. Right? And so the domain expertise that I gained was I learned that you could boost the low signal to noise ratio samples through contrast enhancement. There seems to be a lot of high frequency noise that the whales don't appear at, and so you can come up with features to get rid of that. There's these short, strong temporal features, these strong horizontal or vertical stripes that are probably from shipping traffic or something. And then low frequency noise you can just pretty much notch out. And so the associated engineered features, we have the normalized cross correlation. You can also create a match template for this horizontal feature at high frequency. You can take statistical moments along slices to look for sort of peaky behavior. You can look at the total variation if you see a lot of these different things. And so basically I just tried to create as many metrics as I could that would describe the whales that I wasn't correctly classifying or the samples that I was classifying incorrectly. So the way that I like to think of this is the right thing to do is to do this quick, tight loop of making a prediction, evaluating, and figuring out how you can improve your model versus this sort of random walkthrough algorithm land. And so one of the things that someone said to me after the competition was, I don't have a very powerful machine. I just have my laptop. I couldn't build really any sophisticated models. I used, let's see, I think my computer at the time had something like 8 gigs of RAM, and I just used my home computer. I didn't do anything sort of fancy, and so it was focusing on the data and not just how do I build some crazy neural net. So don't get stuck in algorithm land. Try to focus on putting better data into the algorithm. And so the result of the competition, I won this competition with a friend of mine. Our AUC was 26 basis points over the benchmark, so we got 0.983, which was pretty close to perfect. And then in the follow-on, we got 0.993 because they released more data. And the second place was a speech recognition expert. The top 10 had multiple deep learners. So these are all people, there were some people who had pretty solid applicable experience, and then there were some people who were really good at tuning models. And so it turned out really well for us. And the winning algorithm was I used gradient boosted decision trees. XGBoost did not exist at the time, but I probably would use it now. I had something like 400 features and 12,000 trees. I did a lot of pre-processing to really bring out that signal, and then I had the features that I described before. The only additional metrics were these leakage metrics. It turns out they didn't randomly shuffle their data samples, and so you could actually find periods where you were more likely to see a whale, and so you could bake that into the algorithm. So, but yeah, yeah, it was really the follow-on. There's one guy that pointed out he was able to take the file names and build a nearly perfect classifier just using the file names. That was awesome. Yeah. So real quick, I just wanted to touch on other kinds of problems that you could use this on. And so I like to use it in things where automation is something that you want to do, where you have some sort of manual process that's loosely defined by some set of rules. A good example, I worked on this problem of detecting circulating tumor cells. So a technician sits down with an image, and they have a set of rules for what's classified as a tumor cell or not. And you can pretty easily build a detector for that. And so problems also that are easy to visualize, where you can actually like look at a bunch of data and spot patterns. It's a little bit harder to do in cases where it's like you've got, I don't know, medical claims or something like that. It's still possible. It's just not as easy or intuitive. Yeah, again, just focus on the data and not necessarily the algorithms, and you can actually use the algorithms and data analysis to gain expertise as you go. So, thank you. Questions?
You mentioned the benchmark. I'm sorry.
Yeah.
The benchmark of 0.7. What was that for? Human observation or?
You know, I'm not sure. They I think just had their own code that they were running against. Yeah, they didn't release what they actually did to get that number. Yes.
How much did you win?
The top prize was 8,000. So I split it with my friend. Yeah.
Wow.
Yeah. Any other questions? I tried doing one recently. They had this master's competition where it was like cancer detection, and it was just way too much data without going to the cloud. Everybody that was in the top 10 spent money on EC2 instances and things, and I didn't want to spend any money. So, and there was a lot of people complaining that they spent several $100s and like they didn't win anything, and so that sucks. But yes.
How many competitions you participated?
I think I've participated in like 5 or 6 or something. It's really difficult now, I think, because there's so many more people. So when I did this was like in 2013. And depending on the kind of data, some of the data sets can be really noisy. And so you know, sometimes it's interesting and I'll pursue it. But most of the time it's just to like convince myself that I can still build decent models. And then I'm like, okay, that's good. Oh, yes?
Is your approach still the state of the art, or is there something better now?
I don't know. I would say that mine is pretty labor intensive in the sense that like you're trading computation time for like actually doing analysis, right? Now you've got deep learning that can run on GPUs and things, and so you know, to the extent that that's useful, like then great. But I guess that's not something everybody like can afford or deploy or things like that. Anything else?
What was it that prompted you to start with like decision trees and random forests? Like?
So I worked on this Heritage Health Prize one, and that I used that, and it worked really well. That was sort of where I was introduced to that particular algorithm. But the thing that I liked was I had a lot of features that were strongly correlated, and because I was using like the decision, like I mean, those algorithms are particularly good with dealing with all of that correlation. And so one thing that I did and got a little bit of a boost of was like instead of like doing a local mean removal in 2 dimensions, I would only do it in 1 dimension and then calculate the correlation, and then do it the other dimension and calculate the correlation. And they were just different enough that you actually get a boost. So
like your local test, you have better score or you have lower score than
they were pretty close. Yeah, that data set was actually pretty good as far as like being generalizable. They gave us like 80,000 samples, and I think 70%. Let's see. Yeah, it was like 70%. Like they had a private leaderboard that had 70%, and a public leader, or sorry, public was 70%, and then the private was like the last 30%. Okay, thanks.